In this video, we will be looking at how to determine the molecular mass of a compound. On most periodic tables, the atomic mass for each element is listed directly below the symbol for that element. The atomic masses are essentially how much 1 mole of that element weighs. So for example, 1 mole of oxygen atoms have a mass of 15.9994 grams for each mole. 1 mole of chlorine atoms has a mass of 35.45 grams. We can calculate the molar mass of a compound by simply adding the atomic masses of the different types of atoms. So for example, if we're dealing with something like sodium chloride, the molecular mass of sodium chloride is how much 1 mole of sodium chloride weighs. So we would take the mass of 1 mole of sodium and add the mass of 1 mole of chlorine. So that would be 22.99 grams per mole for the molecular weight of sodium plus 35.45 grams per mole for the mass of chlorine, giving us a total of 58.44 grams for 1 mole of sodium chloride. To determine the molecular mass of lithium nitrate, LiNO3, we would take 1 mole of lithium, or the molecular weight of lithium, 6.941 grams per mole, add to that the molecular weight of nitrogen, 14.01, and 3 times the value for the molecular weight of oxygen, because there are 3 oxygen atoms. So you would add 3 times 15.9994 grams per mole, giving us a total molecular weight for lithium nitrate of 68.95 grams for 1 mole. We can use the molar masses as a conversion between masses and moles. So to go from the mass of something that you would weigh out in the lab to how many moles that is, use the molar mass as your unit conversion, because the molar mass is how much 1 mole of that substance weighs. So the units are grams per mole. We could also use Avogadro's number after that to go from moles to molecules. So we can go from grams to moles to molecules, using the molar mass and Avogadro's number as our prime unit conversions. Because the molecular weight can be thought of as a unit conversion, we can use it to do dimensional analysis. When used properly, dimensional analysis can be used to solve the majority of mathematical problems in this chapter, as well as many of our future chapters. We can use dimensional analysis when working with mass composition or mass percent as a conversion factor, figuring out if we have X grams of sodium, we can determine the number of grams of sodium chloride that are present, or vice versa. We can use information about one compound to determine the information about another. We can also use this to determine the empirical formula from reaction data. Let's now look at some examples of first how to calculate the molecular masses, and then how we can apply those using dimensional analysis to solve useful problems. So our first problem is, let's determine the moles of hydrogen in 1.45 moles of C6H12. For this one, we can just use dimensional analysis. We don't actually have to calculate the molar mass. So we can take 1.45 moles of C6H12. We can multiply that. What ultimately we're interested in is figuring out the number of moles of hydrogen. So we want to have this equal to moles of hydrogen. That is our goal. So we can multiply this by a ratio having the moles of C6H12 on the bottom, and we want to convert this into moles of H. If you look at the chemical formula here, there are 12 moles of hydrogen for each mole of the C6H12. So we could put moles of hydrogen up top, and there are 12 moles in the chemical formula for every 1 mole of the molecule. Our moles of the molecule will cancel out, giving us, as our end unit, moles of hydrogen. Plugging this into your calculator, you will get 17.4 moles of hydrogen are present in 1.45 moles of C6H12. Another problem that we can look at is, let's say we want to calculate the mass of sodium in 6.5 grams of sodium phosphate. So the first thing we would need to do is figure out what sodium phosphate is. Sodium is Na. It's in the first column, so it will be typically Na+. Phosphate is PO4, 2 minus, and so to balance out the charges, sodium phosphate would be Na2PO4 would be our chemical formula. Okay, so we're trying to determine the mass of sodium present in 6.5 grams of the larger ionic compound. So what we need to do is figure out how much sodium there is in the sodium phosphate. So we can use our chemical formulas and dimensional analysis to work this out. What we are trying to find as our answer is grams of sodium. So we can start off with our 6.5 grams of our sodium phosphate. In order to go from talking about sodium phosphate to sodium, we need to have a ratio of the number of moles of each. So to do that, we first have to convert our unit here that we're starting out with into moles of sodium phosphate. So we're going to use the molecular weight to do that. So we would sum up the masses of sodium and phosphate. So that would be sodium has a molecular weight of 22.990. Phosphorus has a molecular weight of 30.974. And oxygen has a molecular weight of 15.9994. So we would take 2 times our sodium value plus 1 of our phosphate plus 4 of our oxygen in order to come up with the molecular weight. When you do so, you'll get a value of 140.9516 grams for each mole of our Na2PO4, sodium phosphate. Okay, now to convert this into sodium, for each 1 mole of our sodium phosphate, we have 2 moles of sodium atoms, right? That comes from the chemical formula. Keeping track of our units, grams here cancels out those grams, these moles cancels out those moles. So we're left with moles of sodium, but we want grams of sodium. So we would take this and multiply it by a fraction having moles of sodium on the bottom and grams of sodium on the top. 1 mole of sodium weighs 22.990 grams. So if we plug that all into the calculator, you'll get 2.120 grams of sodium. Doing our significant figures, that would cut there because of the 2 significant figures for our starting mass. So our end answer would be 2.1 grams of sodium. Our last problem on this one is a chemist decomposes a sample and determines that it is 2.126 grams of beryllium, 7.557 grams of sulfur, and 15.107 grams of oxygen. What is the empirical formula of the compound? Our first step for solving this is figuring out how many moles of each one of these elements we have. So we can take each one of our masses and convert it into the number of moles that that corresponds to. So first we'll work with the beryllium. So we have 2.128 grams of beryllium. And we will multiply this by the molecular weight, having grams on the bottom, moles on the top. You could also think about this as dividing by the molecular weight. So 1 mole is 9.0122 grams. If you plug that into the calculator, you'll get 0.236124 moles. With significant figures, that cuts right here between the 1 and the 2. For sulfur, we have 7.557 grams of sulfur. We will also divide that by the molecular weight, or multiply the fraction with the moles on top, the grams on bottom. The molecular weight for sulfur is 32.065. Our grams cancel out, giving us moles of sulfur left behind, and that is 0.235677 moles. Again, we have 4 significant figures from our initial mass. Lastly, the oxygen. We have 15.107 grams of oxygen. Multiply that by 1 over the molecular weight. 1 mole is 15.9994 grams. That gives us 0.9442229. Significant figure. For this one, we actually have 5 because of our initial mass. So the way we can come up with the empirical formula is by writing out an empirical formula with these values here listed as the subscripts, and then we just need to get it into the simplest whole number ratio. So we have essentially right now, from the information we have, BE 0.2361, S 0.2356, and O 0.94422. Okay, so what we can do is divide these by the lowest of our subscripts, which will convert that one into a 1. So if we divide each one of our numbers by the lowest of the 3, which is the value that goes with the sulfur, 0.2356, 0.2356, and 0.2356, what we get is BE 1.0019, S1, O 4.0064. Okay, because the value for the beryllium is very close to 1, and the value for sulfur and the value for oxygen is very close to 4, in this case, because it is only off in the 3rd decimal place for the beryllium as well as for the oxygen, it's likely that the reason that it is not exactly 1 and not exactly 4 is some sort of a measurement error in our original masses. So this becomes BE SO4. If the subscript is a 1, we leave it out from our end values. This here would be our empirical formula. Because this is an ionic compound, this is also the chemical formula for the ionic compound, whose name would be beryllium sulfate. Let's look at another example. For this problem, we will first be determining the empirical formula and then using that to determine the molecular formula. So, fructose is a common sugar found in fruit. Elemental analysis gives the following mass percentage of carbon being 40%, hydrogen is 6.72%, and oxygen is 53.28%. Determine the molecular formula of fructose. So because we have the mass percentages, what we can do is just assume that we have 100 grams of compound, and from that, calculate the empirical formula. We will then use the molecular weight to determine the molecular formula. So if we have, for carbon, 40.00 grams of carbon, we can multiply this by the molar mass, having grams on bottom, mole on top. 1 mole is 12.01 grams. This gives 3.33056 moles of carbon. For hydrogen, we have 6.72 grams. Again, this is based on assuming that we have a total of 100 grams of our fructose. 1 mole of hydrogen is 1.0079 grams. That gives us 6.66733 moles of hydrogen. For oxygen, we have 53.28 grams of oxygen in 100 grams of fructose. 1 mole of oxygen weighs 15.999 grams. This gives us 3.3302 moles of oxygen. So our formula would be C3.33056 H 6.66733 O 3.3302. We then divide this by the lowest number, which would be the oxygen. Divide each one by 3.3302. 3.3302, 3.3302, and that would give us C. We can see that 3.33056 divided by 3.3302 is close enough to 1. For our value for our hydrogen, that is pretty close to 2, and for the oxygen, this would also be 1. So our empirical formula would be CH2O. The molecular weight for that empirical formula would be, we would take the mass of carbon, 12.01, plus 2 times the mass of hydrogen, so 2 times 1.07, so 2 times 1.0079, plus the molecular mass of oxygen, 15.999, which would give us 30.02628 grams per mole for our empirical formula. We know that the molecular weight of fructose is 180.16 grams per mole of our fructose, FRUC. We want to know how many sets of our empirical formula are there in our overall molecular weight. So we can take the grams per mole of fructose, multiply that to determine how many moles of our empirical formula are in 1 mole of our fructose. So 1 mole of CH2O is 30.02628 grams. Our grams are going to cancel out. So our ratio, if we take 180 divided by 30, we get 6.0007 moles of our empirical formula, CH2O, per 1 mole of our fructose. So that tells us that our complete molecular formula would be, we can take our empirical formula and then multiply all of the subscripts by 6. So our molecular formula would be C6H12O6. And that would be our final answer for the molecular formula of fructose.